Welcome to this session, guys. The topic for today is big data on AWS. So we're going to be implementing particularly two technologies today. So we're going to be implementing your classic AWS cloud service with the EMR, Elastic MapReduce, and we're going to be running Apache Spark on top of the EMR. So all of that might sound confusing right now if you're new to the topic in its entirety. So we're going to be giving an introduction to you step by step as to what these technologies are, what big data is for those of you who are new to big data as well, right? So without any further ado, we can begin. And also a pointer to you guys, since this is a workshop, you guys can ask us questions as well. You can write questions in the questions tab and I'll try to reply to as many of them as possible. First thing that comes up is obviously, what is big data, right? For a lot of you might be new to big data. You might have heard about big data in the terminology, right? This is the introduction to what big data essentially is. So big data is essentially a construct made out of data. Essentially, we need to understand data first as a concept itself. So data is the individual unit of information that is defined as figures or facts and is stored for later processing. So anything that you can store on your hard drive, on your SSD, on your memory stick, that is representative of information is called data from a computer science perspective. So data could be of three types. The first is structured data. Now, structured data is the most organized format of data that exists, right? So for example, you can take SQL tables as an example of structured data. You have proper columns, you have proper rows. You can query that data pretty easily by just simply aggregating a column or by grouping it by some particular attribute, right? So you can do that, all of that pretty easily. So it's the most organized form of data and it's the easiest to query, right? The next up, we have semi-structured data. Now, semi-structured data is somewhere a combination between structured and unstructured data. Semi-structured data has structure to it. For instance, we have CSV files. CSV files have commas that are separating the data points between them, right? So instead of having those column lines like we have in SQL tables, CSV files have those commas between those records, right? So the main difference between structured and semi-structured data is semi-structured data is usually stored in the format of files, right? They are files, while SQL tables are stored in the SQL server as tables and whatnot, right? So semi-structured data can be JSON, CSV, XML. They have a proper formatting associated to them, and you're storing data within them, right? And next up, we have unstructured data, which is completely random in nature. As far as it goes, like if you're dealing with JPG, right? If you convert JPG files, which are image files, essentially, if you open those JPG files with WordPad or Notepad, you'll see a random combination of characters which will not make sense, right? So JPG files don't have any proper order associated to them. They're just a representation of the pixels that are there in that image, and such is the case with PDF, MP3, doc, PPT, so on and so forth, right? So you can convert unstructured data into structured data, or you can convert semi-structured data into structured data. All depends on your algorithm and your comfort level with whatever you have. Let us understand what big data is now that we understand what data is. So there are 5 V's that data needs to satisfy in order to be termed as big data. Now, since the word big is there in big data, one thing is pretty obvious, it's quite large in size. So two particular attributes represent that. So first is velocity. So velocity means that the data that is coming in, right? Say you have a hard drive, right? And the data is coming in periodically, like every minute or every second or every day. And the amount of data that is coming per unit of that time should be extremely large in nature. So that means that the data is like 1 terabyte per day, or 1 petabyte per day, or 90 GBs per hour, or something on those lines, right? The data is coming in really quick. That is your velocity. The data velocity should be really high. And then you have volume. Now, the most obvious factor when talking about big data is volume. So even in stationary form on your SSD, on your hard drive, the data should take a large amount of disk space, essentially. So that means that the data should be anywhere in the upper gigabytes to terabytes to petabytes on your hard drive. Then we have variety. So the data in real world scenarios, when you're dealing with data that is in the terabytes and the petabytes, the data will always be coming from multiple sources, and it may always be coming from multiple file formats as well. It might be a combination of three JSON files and two CSV files, right? Or it could be a combination of two different databases altogether, coming from two different tables. For instance, you have organizations like Amazon, right? So say somebody is trying to create a marketing strategy in Amazon. A data analyst is trying to derive some insights out of the sales and customer figures. So he'll take the customer data set, he'll take the sales data set, he'll combine both of those, and he'll get a aggregated data set, right? That would be his big data set. So that is where variety comes in. Then you have veracity. Now veracity means imperfection. So that means that the data that you're getting should never be perfect in nature, or can never be perfect in nature when you're dealing with real world values, right? So that means the data should have inconsistencies, the data may have missing values, the data may have noise, which means incorrect values, and the data may be faulty altogether at certain points. Because when you're dealing with billions and millions of records in a data set, and you're collecting those samples from real world scenarios, right? There ought to be some data values that are wrong or false, right? So for instance, some people create fake accounts on Facebook. So if you're generating a data set from Facebook, you cannot actually consider the fake accounts as real people when you're developing your advertising marketing strategy and whatnot. And finally, you have values. That means that the data that you're taking should have some value in it. You cannot take some random numbers data set and hope to make some data analytics model out of it. You need to have data should have some meaning out of it. Like for instance, academic student records instead of student roll numbers, right? The roll numbers don't have any value, while the academic records, the grades that they get, have value. You can create some model out of it. All right. So one question that I'm getting is, what is the difference between velocity and volume? That is a pretty good question. So it is not necessary that the data should be coming in, say, every minute or every second. The data could be coming in every day or every month as well. But as long as the data is coming in at a really high volume per velocity unit of time, right? As long as that is happening, the velocity criteria is satisfied. It does not need to come in every second for the velocity criteria to be satisfied, right? Even data that is being stored in a static format can qualify for big data. So yeah. So these are actually 5 terms that you can loosely base the concept of big data around. You don't have to accurately satisfy all 5 of these, right? You might get data sets that are perfect in nature, depending on the method of collection, right? So it might not always be satisfied, the veracity aspect of it. So there are some exceptions, but generally these 5 are followed when we are dealing with real world values. So obviously we have problems when we are dealing with big data. The problems include they are hard to store. The big data sets are hard to store because when you're dealing with big data sets that are terabytes and upwards of terabytes, right? In a normal computer system, you have at maximum you have a 2 terabyte hard drive, and that is on the high end systems, right? Or that is on the high end workstations that you have a 2 terabyte hard drive. So you cannot simply take you cannot simply occupy 1 terabyte of that space with this data set that you're getting, right? That is not a good idea. And petabytes are just impossible to store on normal hardware altogether. So they're pretty hard to store. But storage isn't the only issue. Say, for instance, you have a petabyte hard drive in your computer, which is impossible, but you do have it, and then you store that information on the petabyte hard drive. What happens when you try to process it? You obviously need a very hefty supercomputer like processor to be able to analyze petabytes of data, and even with a supercomputer you cannot analyze it in a short amount of time, in a reasonable amount of time. So even if you are able to store it, you will not be able to process it with 1 or 2 processors, depending on the number of threads and the number of cores that your processor has. So there has to be a solution to be able to store and process big data. So that is the primary issue that was faced in the early 2000s. And then we came up with Hadoop. Now, Hadoop was a technology that was used to tackle this problem. It is a platform used for storing big data across a spectrum of devices. Now, the spectrum of devices means we are not storing that data on one device. We are dividing that data and storing it on multiple devices connected in a network. So that is what Hadoop helps us achieve. Also, The second thing and the most important thing, Hadoop helps us process big data in parallel. So that means that every device will be executing its own block of data that is available to it. So instead of one device executing all of this together in sequence, however the data has been divided, each part has received, each node in the network has received their part of the big data, and they are all analyzing it. They're all analyzing their part only. They are not analyzing the external parts, right? So that helps us divide the time exponentially depending on the number of devices that are there in your big data cluster. It is made up of distributed file system called HDFS and a computation layer called MapReduce. HDFS helps us store it, and the MapReduce helps us process it. Hadoop is also open source, so depending on your versatility in coding, you can also manipulate a lot of variables present within Hadoop. You can create your own APIs with Hadoop. So that is more on the development side of things, not on the analytical side of things. All right, so let us assume we have 4 computers, right? So what Hadoop helps us achieve is that we have 4 computers right now. So we have one computer. These blue boxes are computers essentially. Imagine them as nodes in a network, computers in a network, right? So these 4 computers are connected together through LAN wire. We can imagine they are connected through LAN wire. We can also imagine that they are connected through Wi-Fi, whatever suits you. So these 4 computers are connected together. All of these computers have Hadoop installed onto them, right? This computer has Hadoop. All these 3 computers have Hadoop. So once you have Hadoop installed on top of them, you've told them to discover each other, and you've made one of these computers a name node, and you've made 3 of these computers a data node, right? So imagine you have a file that is too big to store on one data node, right? So it obviously satisfies the case of big data. Imagine it's a use case, right? So the first thing that you will do when you want to store that data, you will contact the name node. So when you contact the name node will scan all of these data nodes. It'll tell you the status of all of these data nodes, and it'll tell you where the space exists, right? So once the space has been discovered, the data node status has been discovered. So for now, we will imagine that all 3 data nodes have space, right? We will imagine that all of these 3 have space. We're not dealing with data nodes that are full in nature. So it will just tell you, okay, contact data node 1 to store block 1 of your data. Divide your data into 3 parts, first of all. So block 1 of your data will be stored in data node 1. The block 2 of your data will be stored on data node 2, and block 3 of your data will be stored on data node 3. So the data is divided into three parts, and each block is stored on a singular data node, right? So the next step that Hadoop does is it will first see if there is a replication factor that the user has configured, right? So for instance, if you're running an HDFS server, you can essentially configure a replication factor. It could be 1, it could be 2, it could be 3, and depending on your use case, you can program it to be more. So for instance, your replication factor is 2. We will imagine here for a second that you've put that variable value as 2. What will happen next? So in order to prevent data loss, in case of any data node going failure, any data node essentially hitting failure, like say this data node fails, we don't want to lose the first block of the data, right? So what Hadoop will do, it will replicate the first block in data node 2 and in data node 3, right? If there are more data nodes and the replication factor is only 2, all of the data nodes will not get the replications, but only the 2 data nodes that are the closest to this data node and have the space will get those replications. So data node 2 will get a replication, data node 3 will get a replication. As we can see, we have green over here, green over here, and green over here. Orange will get the same. Orange, say it went over here, orange went over here, orange will get a replication here, and orange will get a replication here, right? Red went over here, red will get a replication on some other data node that is there in the network, right? And one data node over here. So we've replicated as well. So even if data node 1 fails, it goes bad or something, we still have the backup copies. So we can still access the files. And what the name node will store is where the file begins, the starting point of the file and the ending point of the file in the hard drive, right? So it'll store that. The name node will store that information. So when a client comes and they want to read the data, they want to download that data, they will contact the name node and ask where that data exists. The name node will give them the pointers to the starting and end points, and the name node will also tell the client which data node is the closest to them in terms of latency. So that means that whichever latency is lowest in the milliseconds will be connected with the client, and they will get that data from there in order to minimize any sort of time delay. So for instance, physically, we can see that this client is closest to data node 3. So he will get that data directly from data node 3, and from the data nodes that it can get the data the fastest from. So that is what the HDFS architecture is all about. What are the name node and the data node? The name node essentially is the node that stores the metadata, which means the data of the data, so that's the starting and end points of the data, right? And uh, the data node is where the action happens. The data node is where the processing happens and the main storage happens, right? The name node is not actually storing any data. It's only storing the pointers to the data in the data nodes. And the data nodes are storing the actual blocks of data. And they are interacting via the Hadoop framework that has been installed across the network through LAN wires or through Wi-Fi networks, whatever network there is. So name node and data node here is just a master worker setup. Like this is the master node, and these are the worker nodes. So that is the dynamic that they follow. Don't be confused by the names. They're just master and worker that have been changed in name, right? Intro to Spark. Now that we have discussed what HDFS is, let us understand Spark, right? So Spark is a relevant technology today. Apache Spark is an open source framework that has been developed by developed for cluster-based computing. It was originally developed as an upgrade to Hadoop's MapReduce framework for big data analytics. So MapReduce was a framework that was developed using the HDFS as its base. So every node had the data blocks that they had, right? And the MapReduce framework essentially created a process where they coordinated all of these data blocks together, and they processed them on the node itself, and whatever output came up, the MapReduce framework aggregated that output at the end of it. It combined that output at the end of the job, and it gave you a combined view of the output. So that is what the MapReduce framework was. Spark works on a similar line, except Spark is the technology that we use today. So let us look at what I mean by that exactly. So you had big data earlier on, and it went through MapReduce. The problem at that time when MapReduce was prevalent was that RAM was really expensive, which is physical memory was really expensive. So every time you had to process something, you had to transfer that data from the hard drive to the RAM, and from the RAM to the CPU, from the CPU back to the RAM, and back to the hard drive from the RAM, right? So the time it takes for the data to be transferred from the hard drive to the RAM, if the data was really big in size, the little latency that it took, it all added up to increase the time of the job that it would have taken if say if we were not dealing with this latency at all, right? So that was the main issue with MapReduce, and there was no solution to it because the RAM at that time was really expensive. We could not have bought say 8 GB of RAM for every computer in a cluster. The RAM was really expensive at that time. So the output was received, but with input output delays. What Spark does with the Spark engine, it is a new technology when hardware began to become cheap, right? And RAM began to become cheap. Nowadays, you have 64 gigabytes of RAM in your mobile phones themselves, right? That is how cheap RAM has become today. So the Spark engine uses that. The usage of Spark engine over the traditional MapReduce framework emphasizes on in-memory processing and the usage of shared variables across nodes. So in-memory processing is the key element, the key success criteria for Apache Spark. So what happens today is that you have the minimum of 4 gigabytes of RAM on a computer, and say it goes up to 32 gigabytes, depending on the utility of the workstation, right? The reason we use Spark today is RAM is cheap. So whenever we are having data blocks on our data node, we essentially transfer the entire data block, if possible, onto the RAM. And until the job is complete, until we have completed the job, we keep that data on the RAM itself, right? We are not, putting it back on the hard drive, or we are not taking it from the hard drive again. So until the job is completed, the data stays on the RAM. So there is virtually no latency between the CPU and the RAM. The processing happens, the intermediate outputs come out, and after the final output comes out, you have the option of storing it back into the hard drive. So in theory, there are essentially only two interactions with the hard drive. So that reduces the time taken to complete a big data job drastically, about 100 times faster. It makes Spark about 100 times faster than MapReduce with in-memory processing, because RAM is cheap today, right? So this is not visible for small data sets, mind you. This is only visible for actual big data sets, because in small data sets, you will not notice the difference in time. But when you're dealing with big data sets, you will definitely notice the difference in time. And it could be about 100 times faster. So let us move on to the cloud now that we have a little background on the technologies and the stacks we are going to be using today with AWS. So Elastic MapReduce is one of those technologies. Now, Elastic MapReduce, it's just a fancy name. It's just one of the services that AWS provides as a cloud service. So this is the traditional way of implementing big data. You are a client, right? You want to access a big data cluster to complete your job. You write your code and you basically send that code and you deploy it onto the big data cluster. The big data cluster analyzes your output and gives you back the answer that you need. So this is the traditional way of going about it. This is your big data cluster. What Amazon came up with is a cloud service to implement that. So for instance, let us imagine you're the client over here on the left hand side and you have an AWS account. You go to your AWS account, you open the EMR service, which is the Elastic MapReduce service, and you deploy your cluster, right? So what this does is you don't have to install Hadoop on any computers. You don't have to do anything manually, right? Most things Amazon will do for you. It will create the cluster of your desired size, mind you. So if you've entered the size 4, it will create a cluster that has 4 nodes, right? If you entered an auto scaling mode, it will create a cluster that changes the size depending on the workload, right? So the main advantage that you get with this, it's fully managed. AWS manages all of the security updates. It manages all of the software upgrades. It manages all of the version upgrades. You just have to click a single button. So the administrative job essentially becomes none, right? You don't have to deal with the administrative job for at least mid to low tier jobs that you may have with regards to big data. You don't have to deal with any of that installation, maintenance. You don't have to have a maintenance team for that. Abstract visibility, AWS manages all of it on its own. One question that I'm getting particularly is what does it mean by it increases or decreases the size on its own? So that is a essentially what auto scaling means. So Amazon is self-aware of how much workload there is for that particular job, right? So for instance, you have a job that requires more nodes in your cluster. You have only 4 nodes. You are trying to execute a job that has like 5 6 nodes that requires 5 6 nodes. Amazon will automatically detect that and it will increase the size of your cluster in its practice itself. You don't have to go there and manually do that. And say for instance you don't need those 6 nodes anymore. Amazon will manually decrease the number of nodes that is being executed that are being used for your job. So this is also to basically provide you with efficient pricing, right? For instance, if you had a locally housed big data cluster in your own office, you would have to pay rent for the entire server for the time that you had it in your office, right? With Amazon, you only pay for what you use. So that is the main advantage with AWS big data on cloud, essentially. So this is what the AWS console looks like. It's a pretty, I find it to be the best cloud service there is, AWS, hands down. There is Google Cloud, obviously, and there's Microsoft Azure. Both have their own advantages, right? But I found AWS to be an all-rounder when it comes to pricing and when it comes to the plethora of services that it has. Like for instance, if you go to Google Cloud, you'll go to the Mumbai region, right? For instance, there are a lot of there are less resources that are available in the Mumbai region. So whenever you try to create any instance or something, it does not actually create, and you have to go with Singapore or something. So I think AWS has their things really figured out. So firstly, we have this little convenient option over here to select from the plethora of services that AWS provides. Right, we're going to be going with EMR today. So this is Elastic MapReduce. As you can see, I've already experimented with this a lot. These are my cluster histories, right? And I can simply go to create a cluster for a new one. So we can see how convenient this is. We can name our cluster anything. So firstly, let us call this workshop, right? So that I keep track of what this cluster is about. And then the other thing that you can focus on here is there is these are available here over. These are software packages. You can install Core Hadoop and Hive and Hue and other big data services, or you can go with Spark, right? So these are the 4 pre-selections that there are. You can also go in the advanced options to basically select a more custom sort of software installation package that you need. You can install Jupyter on it, right? There is HP, Espresso, Scoop. You obviously have Spark. You have TensorFlow for those of you who are interested in machine learning. You can install all of that. It will install on its own. So that is how convenient it makes it. So you don't have to go to your command line terminal and install this, install that, and install it on 50 other computers as well. You don't need to do that. You only need to select it over here, and it will install it automatically. So we go back to the quick options again, and I want to select a pre-selected package with the bare minimum that I need. I need Spark, I need Hadoop, and I need Yarn. I don't need Zeppelin particularly, but it'll just get installed. It's not an issue. So I can select the machine type. So these are the machine types that AWS gives you, right? So for instance, there are a lot of instances that AWS can give you. Some are compute optimized. So that means the processor in these instances is really strong. Some are storage optimized. That means that these particular instances have good storage. Some are GPU instances. That means that graphics card in those instances are really nice. These are good for machine learning, probably. There are storage optimized instances. So you have general purpose instances. So that means that if you're practicing or anything, if you don't have that big of a job, you can go with these. You have memory optimized instances. That means the RAM in these instances is really fast. All of these instances have different pricing. So be sure that you don't mess around with these settings too much when you're practicing. You only need the bare minimum that you need for your practice sessions. So I'll just go with the M5 X large, which is default, and I don't need two core nodes. I'll reduce this to two so that I get one master node and one core node. So this is the one core node is the data node, and the one master node is the name node. So I think you can correlate it. And there's the option of cluster scaling, which I talked about earlier on. So that means you can increase or decrease this cluster size depending on the workload. There's that option over there. And these are the security settings. So in order to get into the master node, right, I need a key. So I've already pre-configured a key, which is workshop underscore EMR. Actually, not workshop key is the EC2 key pair that I've already configured so that I can SSH into the cloud system. So with that, then I'll just simply create it, and it will take some time to create. So meanwhile, please, guys, you can ask us any questions with regards to all of this. So the machine learning capabilities in AWS, there are a lot, right? So for instance, while this is starting, I'll just show you this over here. And the main advantage of this is that you can integrate it with EMR, you can integrate it with other AWS big data services or AWS services in general. So SageMaker, right? So this is Amazon SageMaker, right? So this is the most convenient tool I have found for machine learning yet. Obviously, if you're analyzing large data sets, it will take some pricing to get it out, but it's good for practice as well if you're just doing it for practice, right? For instance, you have the SageMaker Studio. The main thing that I do for practice in Amazon SageMaker is I go to notebook instances, right? And I can start a notebook based on any sort of cluster that I have, or I can simply create a notebook instance. I can analyze, I can select the machines that I want for my machine learning notebook, right? And it will simply open up a Jupyter notebook that you can use with Python. You can install TensorFlow on it. You can use the libraries of TensorFlow. You can create your own machine learning model on the Jupyter notebook itself, right? So these are the various features that you get with it. Secondly, there are other options as well. If you go to EMR, which we are doing right now, there is a notebook option over here as well. So if you have a complex machine learning task, which is dealing with big data as a training set, you can go to notebooks, you can go to create notebook, right? And you can choose a cluster that you want to run it on. So for instance, my cluster is currently starting, right? I can select that and I can click on choose cluster. So my Jupyter notebook will start on top of this entire big data cluster that I have just created. So whenever I run a machine learning training job, right, it will use the resources available throughout the entire cluster. So you can imagine if I have assigned GPU optimized instances for my cluster, how fast that job will go, right? So for creating machine learning models out of big data, you can definitely go with Amazon EMR. There might be an issue with the region over here. So some regions do not actually allow notebooks. So for instance, I don't think Mumbai allows notebooks. So you can simply switch that up to say US, North California or Oregon. That will work as well. So it's starting currently. I think it's running now. Yeah. So my cluster has successfully started. I forgot to change the name again, but yeah, it's called my cluster for now. Okay. So any other doubts? I will be continuing now. So if anybody has any doubts, you can ask me that as well. The other thing that I would like to mention over here as we are moving ahead with the session is that data analytics on its own is not that lucrative of a field. For instance, if you're simply understanding how data analytics works and you're applying for a job, you'll not fetch that high. But when you understand how big data works, right? Whenever you get to that point where you understand how big data works, you certainly have an edge in the industry because you're not a simple data analytics expert anymore. You are a big data analytics expert, and you can implement that knowledge with data science. You can implement that knowledge with machine learning, and you can implement that knowledge with artificial intelligence, which are three of the most popular and lucrative fields in technology today, right? So you can imagine the edge that it gives you. So for instance, let us continue with this. I'm being asked question, can we rename the cluster? We cannot rename the cluster. So that's kind of some things that we can't do in AWS because of some reasons. We can't actually, as far as I'm aware, we can't rename the clusters. So I want to connect to my master node. So I'll go to enable an SSH connection, right? And I'll copy this link, the host name. I'll put it over here, right? So the port is 22 for SSH. Go to SSH in general and I'll give the key. So my key is workshop key that I had created earlier. These are not that complex. They're just keys that you generate, and these are unique keys, private keys that help you connect to the terminal. We go to tunnels, we add a port. We want to open a port up basically. So 8157. These instructions are available on Amazon's website as well. And we change this to dynamic and we click on open. Yes. So as we can see, so command line terminal that I've opened, I've connected to the name node of my Hadoop cluster. Right? So we can see that it is there. We can type anything on it. We can type ls, which are normal Linux commands. There is nothing in the present working directory. We don't know what is there. So yeah, the next thing that I can do, firstly, I'll just increase the size so that you guys can see clearly. Change settings. I'll go to appearance. I'll go to the font and I'll put this to like what I think 18 should work for now. So that is quite big. I'm not entirely sure. I'll just decrease it a little bit. 16, I think, should suffice, right? Yeah. So yeah. Next thing that we can do is we can start a Spark cluster. Not a Spark cluster, actually a Spark session. So we'll type in Spark shell for that. And remember, we had actually selected Spark when we were installing, when we were creating the cluster. So it is there by default. We don't need to install it. It takes some time to start, but it's initializing the resource allocation yarn, and then we'll get to the terminal. So the Spark session is available with the variable Spark. So whatever operations we're going to be doing, we're going to be using the Spark variable because this represents the Spark session variable, right? Okay, so this is only valid for the session. Whenever I exit this command line terminal, all of the memory that this particular session is taking will be automatically given to garbage collection. So it will be freed up automatically. This is only temporary. This is all in the RAM, as we were discussing earlier, in memory processing. So I'll just minimize this. This is quite distracting actually. All right. So firstly, the thing that I'll do is I'll go to my management console. I'll open up S3. Now, S3 is exactly like Google Drive in a lot of ways. You can store your data on S3 and you can get links from S3 as well. For instance, we have a lot of buckets created. We can create a new bucket if we want. Right? We can go with, let's call this workshop Spark. We can select the region. And we'll disable this at the block all public access because we want to be able to access it. But when you're dealing with more secure sort of organizational environments, you'll have custom rules set for your S3 in where you wouldn't have to block all public access, right? You can actually block all public access and still be able to access the bucket. So I'll acknowledge that. And then I'll simply go to create bucket. Quite a simple procedure. It's like creating a folder. So we'll just search for workshop Spark. and we'll upload something. So let us upload a data set. So currently let us upload this yellow.csv, right? So I'll just open this up and show you guys what this is actually. So this is kind of a taxi data set, right? These are like cab summaries. You know, when you go to Uber or Ola, the data set that is generated, this data set sort of mimics that, right? This is the number of passengers that were there in the car and the trip distance, the pickup latitude, the rating that the person got, the driver got, and the dropping latitude, longitude, the payment type. So one could stand for offline, two could stand for online payment, the fare amount, extra MTA tax, tip amount, the total amount, the tolls amount, the total amount, and the trip time. So this is, I think, in seconds. Right? This is in seconds, the trip time, probably. Not exactly seconds, I would say. Yeah, this is in seconds. Definitely in seconds. Okay. So yeah. So let us continue with this. Okay. We now know how the data set looks like. Right? So we'll select this and put it over there. And we'll see, upload this. So we've successfully uploaded yellow.csv, which is a comma separated value file. And we can get this link over here, which is the S3 URL. So this is where we can access it when we're using Spark. So any doubts up until now? All right, so no doubts. Okay. Let me just continue now. So what I'm going to do first is I'm going to be creating a data frame. So data frame is quite similar to like an SQL table, but except we are doing it over here in Spark. So it's also quite similar to the Python data frame as well, if you're aware of that. For those of you who have done Python, you might be knowing the pandas data frame that Python has. Except here it's all memory optimized, and if the data set is really huge, the data is divided on multiple data nodes, right? It's still picked up as a common data set from all of those nodes, and it's viewed as a common data set in the Spark terminal that you're trying to execute it on. So let us call this val df. So val is something you use in Scala language, right? And df is a variable name. Spark dot read dot format. We put in a CSV over here because we want to specify that the format is a CSV file. Option, we put in an option which is header comma true. We want the headers to be included in our final data frame. We can add another option. Let's call this option infer schema. Now infer schema means that whenever we put it to true, it will automatically detect the data type of each column so that there are no issues with that. And option over here, we can add an exception case. So if there is an exception in the execution of the statement or the creation of the data frame, it will automatically throw it and show what exception it is. Dot load. Now load will include the paths to the S3 bucket. So I did not actually copy that. Again, I'll need to copy that and put it over here, right? So we've specified the path as well, put it up, and then we simply execute it. Hopefully this executes and there is no syntax error. So we can see there is a progress bar that has been created. So that basically represents how much of the loading of the data has been done. So we can see that it has been created. We have automatically detected the columns as end and so on and so forth, right? And we can just see how it looks like. So df.show, we can see just like two data records so that we don't actually crowd the screen. We don't actually flood the screen with data. So it's actually kind of messy, but we'll try to look into it. So we have vendor ID, we have the pickup time, drop off time, passenger count, so on and so forth, right? And it's kind of misarranged because I have increased the font size so much. So ignore that for the second. Okay. The next thing that we can do, even if I decrease the font size right now, by the way, it will still not rearrange itself. So that is an issue with command line terminals in general. So the preferred way to do this would also be to use the notebook. But since the Mumbai region does not have the notebook option, I would rather just do it with the terminal for now. Question: what is the required AWS knowledge required for this course? None. You don't need to be a master in AWS to be able to implement this course because all technologies relevant for big data on AWS will be taught in the course itself, right? So you don't need to basically deal with any additional technologies like security VPCs and whatnot. All of the technologies relevant to the course will be taught in the course itself, and they're pretty easy to understand. So you don't need to deal with the rest of the AWS. You don't need to become a cloud practitioner to be able to execute this. Can I give any public URL rather than S3 bucket URL for the CSV? So in order for that to work, you need to give a URL for a file, right? The problem with Spark is that it's compatible with only file systems, and S3 is a file system. So you cannot simply give a URL like a link. You cannot simply do that on the internet and expect it to basically work. You need to put it somewhere, and then you need to provide the link to that directory in the file system. You cannot do it directly from the internet. So for instance, I did not. There are two links available actually over here. If we go over here and look over here, for instance, so there are two links. So one link is this that we just talked about, which is the S3 URL. The second link that we have is this, right, which is the object URL. So when I'm not using this link, the HTTPS link I'm not using. I'm using this link. So I hope that makes it clear. Okay, so we can perform some analytics with it. So let us look at the data set again. For instance, where's the data set that I put? So here we can see, if I simply expand this, this is how the data set looks like, right? So for instance, if I want to count the number of trips that have been taken in according to this data set, so what will I do? The first thing that I would do is definitely register this particular table in the SQL context that Spark provides. So if I'll simply type, not spark.sql actually, first thing that I will do is df.create or replace temp view. So we are creating a temporary name in the SQL context for this data frame, and we'll call this taxi. Let's call this taxi for now, and we'll close that and press enter. So now we can refer to this in the SQL context as taxi. What is the SQL context? You may ask. If I simply type spark.sql, we have actually virtually created an SQL environment just so that we can execute and query this data frame with SQL queries, right? So that is the advantage of it. If I type in something like in a normal SQL query, like select count asterisk from taxi, I close it up and type in dot show. I can put in a bracket over there and I press enter. So it will count all of the number of columns, number of rows that there exists in this data set, and it will give me that answer. So we can say that it's about 10,000. Right? So it's a 10,000 record data set. In real world cases, it might be in the millions to the billions, and you'll still follow the same process to do that, and it will still take roughly around the same time to do that. That is the advantage of it. So depending on the cluster size, obviously, if you have only one or two nodes in your cluster, and if you have a petabyte file, you cannot obviously do it in this less amount of time. But depending on the nodes, the job will be divided equally, and it will be executed across all of the nodes that are there on your cluster. Then the next thing we can do is spark.sql and say we want to calculate the average fare of a trip, right? So we can look at the column name that we have over here, the fare amount, which is fare underscore amount. And if you want to calculate from an analytics point of view, what is the average fare for a trip for my taxi service, right? So I'll type and select average fare amount from taxi. I'll put it over there and pass the query, type in a dot show to see the results, press in and enter. It'll evaluate it and give me the answer. So yeah. So any SQL query that you can possibly think of. So if you want to simply spark.sql, select average total fare, I guess called total amount. Just check 1 second. For the total amount, yeah. So this is the amount after all of the taxes and the tolls and everything. So this is basically the sum of these amounts, I suppose. Yeah, whatever it is, we're just calculating the total amount. It depends on whatever the analytics question is. So from taxi, and then I can do something complex with it. We can go and say, for instance, I want to group it by the passenger number. Depending on the number of passengers that there can exist in a car, I want to group this total amount based on that, right? So I can do that as well. So I'll just see the column name. It's called passenger underscore count. Got it? I'll go over there, put in a comma over here and type in passenger underscore count. And I'll go over here and type in group by taxi not taxi, group by, I think, passenger count. Close this up, dot show, and press enter. So we can see that if the passenger count is 6, I think these are minivans in all probability. These are big cars. So if the passenger count is 6, it's about 15. For 1, I think it came out to be 16. For 0, which is something I don't understand why there's a fare for that, but I guess okay. I'm not sure about why there is a 19 for 0 passenger count. Something in the data set maybe. Okay. So other things that we can do with it, spark.sql, I just bring the previous statement up rather than typing it again and again. I can provide aliases to column names. For instance, here we can see that there's an average total amount. This looks sort of ugly. I want to change it. So I'll type in as and provide an alias to it. So let us call it average underscore amount. Right. So that is my new column name for that. I'll go over here and add an order by, and then put in the average underscore amount. So the moment I do that and press enter, it will arrange in ascending order of the amount, the average amount that it takes. So we can see the lowest amount is for 6 passengers, which is quite odd. The second lowest is for 4, 2, 5, 1, 3, and 0. So that way we can arrange it as well, right? So normal SQL, you can implement it with Spark SQL. That is how easy this is. So if anybody is coming from an RDBMS background, basically an SQL background, they can feel right at home with this particular part of the analytics procedure with big data, whether it's on cloud, whether it's offline, right? Where as long as you're using Spark. So that is why Spark is one of the most amazing technologies out there. You cannot do this with MapReduce. MapReduce takes a lot of Java coding or C++ coding, right? Here, you don't need to do anything at all. You can create a virtual SQL context and you can simply go ahead and run your SQL queries on it. So any other thing that we can do with it. So for instance, let me look at what we can do with it. So we can perform some analytics with it. We can see what the average trip distance is, or I would say what is the vendor ID for the average, we call it, make questions with it just a moment. So let us go with the trip distance over here. So let me take the trip distance column and the payment type column, right? So let us go with that. What we will do now is we will calculate the average trip distance for each of the payment types. Spark.sql, select average trip underscore distance as average underscore distance, and the payment type, obviously payment underscore type, which is I think the column name over there, from taxi, group by payment underscore type, order by average underscore distance. It by default arranges itself in ascending order. So we do that and we put in a dot show over there, bracket open, bracket close. So there's an error. I think I did something with the syntax that was not supposed to be done. So table or view not found. Line 1 position 66. What did I do wrong? Select average trip distance. Okay, okay, all right, I got it. So thank you for the assist. Yeah, so I misspelled taxi over there. So thank you for the assist. I'll go back and I'll correct the spelling. Thank you for the assist. Yeah, so it's I, it's not T, and then I press enter. We go by that and it executes. So we have it. So for the payment type 1, we have 3.5. For payment type 3, we have this. So this could be cash payment, this could be debit card, this could be online wallet payment, this could be something like pay later or something, right? So there are different payment types in your mobile apps these days for these services. So that's there. So basically we get that.